In this video, we explore infinite limits. I want you to consider this function f of x is 3 divided by x minus 2. And we notice pretty quickly that when x is equal to 2, my function is undefined. So x equals 2 is outside of the domain. X cannot be 2. And I want to explore what's actually happening around 2 there. You might already have some ideas, but I want to do it in a calculus sense with looking at some limits. Really what I'm interested in here is what's the limit as x approaches 2 of that function. And in a situation like this, we tend to look from the left and from the right. Okay? We can analyze this kind of by hand. There's not a lot to write down when we do that. So what I'm going to do is bring in the table here. I've got values for you. And as x approaches 2 from the left side here, we see that my function seems to be getting more and more negative, right? I would imagine if I plugged in another 1.99999, kept going, I would add zeros to that negative 3,000, it would be like negative 30,000, and so on. We say that the function decreases without bound. Okay? And in that situation, we can really write that limit as minus infinity. That's just going to keep getting more and more negative. Okay? Now, from the right side of 2, we see that the function has a similar kind of behavior, but this time it's not decreasing, it's increasing without bound. And we write what we say is positive infinity. Okay? These limits are infinite limits. They're limits that result in either plus or minus infinity. Okay? And they will denote some different, they will mean some different things. But technically, then the overall limit here actually does not exist. Okay? And that's because of the definition of the limit. We'll touch on that on the next slide here. In fact, the limit as x approaches c of f of x in general, if that's plus or minus infinity, that doesn't mean that the limit exists. And that's because plus or minus infinity is not approaching a specific number, a single value, right? So really what this limit is telling us is that the function, that the limit, fails to exist by denoting what we call unbounded behavior. Okay? And that unbounded behavior is beneficial to us. Instead of just saying does not exist, we can tell about the behavior of the function, and that's useful information. For example, if I've got some curve here around C, I see that to the left and to the right, I've got unbounded behavior, but I can still tell what the function is doing. And I can describe that. As x approaches c from the right, we say f decreases without bound. And as x approaches c from the left, f increases without bound. Right? And we typically explore this in a left or right-handed limit, right? But that gives us useful information. It gives us an idea about the behavior of the function. Right? So I want to look at another function here, 1 over x minus 1 squared. We quickly see that when x is 1 here is when I would have a domain issue, right? So that's the x value that I'm interested in. I'm going to go right to the left and right-sided limits here. Let's look at the limit from the left as x approaches 1 of 1 over x minus 1 quantity squared. Okay? And I'm going to try to analyze this one without the table. What I like to think about is when x is approaching 1 from the left, my x's are less than 1, right? My x's are less than 1, but in the denominator here, I've actually got something squared, and that's always positive. I really want to pay attention when x is less than 1, what's happening in my function, right? Is the numerator positive? Is the numerator negative? Because that's going to have some bearing on how the function is behaving. In this case, the denominator is squared, so it's always positive. Okay? Numerator is also positive. As x is approaching 1 from the left, the numerator is going to 1, and the denominator is going to basically 0, right? 1 minus 1 squared is going to 0. And the way I write that, or the way I think about it, is to positive small values, right? I can't take away the fact that the function is approaching 0 in the denominator, right? So I'm dividing by 0, which is bad, yeah? If I keep plugging in numbers that get closer and closer to 1 from the left, right? 0.9, 0.999, 0.9999, subtract 1 and square it, I've got a positive number that's very, very small. And when I divide by that very, very small number, things get very large. Okay? So that should actually be not a negative infinity, but a positive infinity. I'm sorry about that. Everything is positive that I'm working with. So from the right, I get a similar type scenario. I try to do the same type of logic here. As x is greater than 1 when I approach from the right, but again, my whole function here is always positive, right? And though even from the right, I'm dividing by things that are getting smaller and smaller, the numerator is going to 1, denominator is going to positive small, I'm still seeing a positive infinity. So together then I can say that these two limits kind of match, which means my function looks like it's approaching infinity. Right? Technically, either of these together do not exist, right? And that's because of what we saw in the previous slide. The limits themselves aren't approaching a single value, so they don't exist. But my function here then, as x approaches 1 from either side, oh, that's wrong. That should be up to positive infinity, forgive me. Positive infinity. Oops. And as x approaches 1 from the right, my function approaches positive infinity as well. So I've got this kind of volcano-looking thing. This line here, this imaginary line, is what we call a vertical asymptote. Okay? You've seen vertical asymptotes before. But the new thing here is that they're actually limits, right? They have a limit definition. Okay? Vertical asymptotes have a limit-based definition. And I want to go through exactly what that definition is. From what you know so far, you basically have just looked for zeros in the denominator. And that's not really going to change. I'm not going to take that away from you. That shortcut is still available to us. But I want to show you kind of why things are the way they are and how it pertains to these infinite limits. It's really kind of the backbone of what a vertical asymptote is. Vertical asymptote here, I will commonly shorten that as VA. Okay? The definition goes like this. If f approaches infinity, either plus or minus, as x approaches c from the left or the right, doesn't matter which side I'm approaching from, then the line x equals c is said to be a vertical asymptote of the graph of f. So if I approach plus or minus infinity from either side of c, then my function has a vertical asymptote at c. Okay? There's like I said, another way to describe this, and as you know, it's with having zeros and denominators, typically what we're looking for. It doesn't have to be the only time we have vertical asymptotes. But in short, if I've got some h of x, which I describe as f over g, I've colored it the same, but these f and g's aren't these f's aren't necessarily the same. Just a placeholder, right? If my function is described as f over g, and I can observe that f of c is not zero, while g of c is 0, then we can say that the graph of h here, my function, my rational function, has a vertical asymptote at x equals c. Okay, so again, I'm still looking for zeros in the denominator there, but the key is that I can't have 0 in the numerator. I'll try to explain what happens when I do have a 0 in the numerator as well. Just a basic example here, say h of x is 1 over 2x. Okay? We see that the denominator is 0, when x equals 0, of course. But the numerator is not 0 when x is 0. All right, and that's directly the situation I'm in up above here, where f of c is not 0. F of 0, the numerator, is not 0. So x equals 0 is a vertical asymptote for this function, right? I can argue that from the left and from the right, my function is approaching either plus or minus infinity, or when x is approaching 0. A slightly different example here. Say h of x is x over x squared minus x. A little different. I can observe that the denominator here approaches 0 when x is either 0 or 1. Yeah? If I plug in 1, 1 squared minus 1 is 0, or 0 squared minus 0 is also 0. Okay? But the numerator is only 0 for one of those. It's not 0 when x is 1. Okay? So the numerator is not 0 when x is 1, while the denominator is 0 when x is 1. So x equals 1 has to be my vertical asymptote there. But what about when x is 0? The numerator is also 0 when x is 0. I don't have a good idea about what that means. What can I say about x equals 0? Up until this point, you've kind of been told that when there's zeros in the denominator, you've got vertical asymptotes. But these situations are particular ones, okay? So what's going on here when both f of c is 0 and g of c is 0, or the top and the bottom are both going to 0, we have what we call an indeterminate form. And that means we're going to have to investigate further. We gotta investigate. We don't know exactly what's going on yet. I'm going to detach from that last example for a minute. I'm going to kind of go through a new one. If I've got some function here, p of x, described by x squared plus 2x minus 8, divided by x squared minus 4. Okay? I'm going to try to figure out when the numerator and denominator are 0 here. X squared minus 4, I know factors as a difference of squares. Numerator factors to x minus 2 times x plus 4. And here's where we see that the denominator would be 0 when x is 2 or negative 2. So I say x cannot be 2 or negative 2. Those are my domain restrictions, right? What's going on at either of those places? Well, let's see. I'm going to take a limit as x goes to 2 of this function. Okay, I want to see what the behavior is as x approaches 2. And we can quickly see, since I've already got it in factored form there, that we're going to cancel. But first, I notice that my numerator and denominator are both going to 0. Okay, so I have an indeterminate form. There's probably something else going on here. So I can cancel these x minus 2's, leaving me with x plus 4 over x plus 2. And as x approaches 2, it looks like I have 6 on top, right? 2 plus 4 is 6, and 4 on the bottom. Simplifies to 3/2. That's definitely not an infinity. That's definitely not an infinity. So when x is approaching 2, I don't have a vertical asymptote there. There's not a vertical asymptote when x is 2, because that limit is not plus or minus infinity. Okay? At negative 2, this is called then, before I forget, a removable point. A removable point because I can cancel, and that 0 over 0 is now gone. I don't have it anymore. It's removed. As x approaches negative 2, however, I make a similar cancellation, right? The top is going to negative 8. It's not going to 0. Okay? So I don't have an indeterminate form here. The cancellation we make is kind of fruitless, because as x approaches negative 2, I haven't taken away the fact that the denominator is still going to 0. The numerator value has changed a bit, but it doesn't really matter. I'm still dividing by numbers that are approaching 0. And we know from the first kind of example that that's going to have some effect that's either plus or minus infinity. I can explore As x goes to -2 from the left, we're able to show that my function approaches positive infinity. Okay, you'd have to dive a little further, whether you use a table or the kind of logic I did on one of the first two slides was I said that x was less than 2. So as I take something less than -2 and I add 2 to it, I've got negative values. But on top, I also have negative values. So that should be a positive infinity. Similar idea as x approaches -2 from the right, I've got negative values, and actually I think these infinities are backwards. But regardless, I believe this one should be minus and this one should be plus. Regardless, we end up in a place where from either side of -2, my function is approaching one of the infinities here. The limit does not exist as a whole, but I know enough to say that x equals -2 is a vertical asymptote. Okay? So again, that limit definition prevails, and it says that if I approach either plus or minus infinity from either side of C, then C is a vertical asymptote. If the indeterminate form can be removed by cancellation or something like that, then you're probably not talking a vertical asymptote. Sometimes you can be, but often not. Often it's a removable point or something else. Okay. Going back to the example on the previous page, we know how to handle now when h of x is x over x squared minus x. So from before, we said that x equals 1 was a vertical asymptote because the numerator was not 0 and the denominator was. So when x is 0, both the top and bottom are approaching 0 here. That's that indeterminate form. So we look at our limit as x approaches 0. We can factor the denominator and we can cancel and end up with the limit as x approaches 0 of 1 over x minus 1. And as x goes to 0, I'm just approaching -1. Okay? This is another removable discontinuity. Okay? There are loads of other examples where I have limits that are approaching plus or minus infinity. All of the properties of limits here are still available to us. So the limit properties that we have, limit properties, are going to remain. Okay, those aren't going to change, right? I'm still able to take a limit of a sum or a difference and break it apart into two separate limits. But for the most part, we want to try to be able to analyze and determine when a limit is going to be infinity or minus infinity. Again, try to remember that the limit technically doesn't exist, but we're able to say how it doesn't exist, right? Is it increasing or decreasing without bound? Right? That's really it for this video. Thanks for watching.